Hello, our fabulous chemistry students
MoNaCo is here.
and Milks, and we are still in that last unit,
Fourth homework lecture,
page 8. Let's look at that nucleus.
and see what's happening when we're talking about radioactive emissions. What are these?
Right.
And why?
Here you go. So first, why some elements are radioactive. They basically don't have the right ratio of protons and neutrons. They can tend to have too many protons in a small little space.
Yep.
And that magic number turns out to be 83.
I think of this myself as like a Jenga tower. Okay, a short Jenga tower is very, very stable.
Okay.
Or a short stack of bricks, a short stack of textbooks, very stable. The bigger the stack gets,
The more it might fall over.
the more likely it is to fall over with a small bump. So the atoms that are very large and heavy, their nuclei tend to be more unstable.
Okay.
That's how I think of it.
All right. Well, we got some examples here for you.
So this is uranium isotope 238, and it is becoming naturally
Thallium.
thorium.
Thorium, I was close.
For Thor, the god of thunder,
Nice.
the Norse god of thunder, one of the Avengers.
Yeah, he is one of
Yeah,
the
one of the Avengers. 234. So you see the atomic mass on top has actually changed from uranium to thorium by 4 units. Where the heck did it go? It released an alpha particle that had the mass of 4, and that's what the little A, the Greek A, looks like.
Yeah,
alpha
with
particle.
the 4 and the 2. And just as a little precursor for what's going to happen, this is some of the math we were talking about. And the numbers on the right side add up to the numbers on the left. That adding and subtracting is
all the math
mad.
you got to do this unit.
Mad.
Oh wait, no, we got to do fractions for half.
A little bit of fractions for half.
But we'll get there when we get there.
One more example.
We got radium 226, naturally unstable,
Is that
becoming
radon?
Becoming radon,
Oh, I got one right.
and a helium nucleus, which is the same mass and charge as an alpha particle. So they're the same thing.
They are the exact same thing. So I wanted to have one of each up there for you, so you get an idea.
Don't
what an
let
alpha
the
particle
atomic
is.
symbol being alpha versus He throw you off. They're really the same thing we're talking about.
And they're both in the reference table waiting for you to see.
So there's some examples of atoms that are heavier than atomic number 83.
All right, let's look at specifically alpha decay. This is going to happen when an unstable nucleus emits specifically an alpha particle, which of course consists of 2 protons and 2 neutrons, making the parent molecule more stable. So here's a little picture of a nucleus losing its alpha particle, and this is where you see alpha particle in your table O.
And all the notations and symbols, right?
Beautiful.
That's it. Beta decay. Now, a neutron becomes a proton by emitting an electron. So the emission is an electron flying out. But what also happens is that the atomic number will go up, interestingly, but the atomic mass does not change. So you'll see that when we're balancing some equations in the next video.
And this one's interesting.
What happens with it? So essentially a beta particle is an electron, but it's an electron that gets emitted out of the nucleus. So this is not just like I'm losing an electron, because we'd call that ionization.
Right.
This is the nucleus emitting an electron because of what had changed inside with the protons and the neutrons.
Right. Well, if you lose if a neutron, which has a neutral charge, loses a negative charge, it ends up now with a positive charge.
So this is how protons are formed and electrons are formed.
Right. And if you look at the notation real quick, you see the E with the -1, that's our normal electron. And then the B -1, which is that beta minus. Okay, so again, synonymous.
So then gamma emission, and Mr. Milks had to do some research on this because we don't see it in nuclear equations. Why don't we see it in a balancing nuclear equation, Mr. Milks?
You tell me, because this one's crazy.
Well, there's no atomic mass or atomic number. This is just pure energy. So we don't balance equations to show pure energy. We balance equations to show mass and charge. And since gamma radiation has neither mass nor charge, it is purely a photon of high energy. So it doesn't really come into our nuclear balancing at all.
No, what it really comes down to is in our definitions and our penetrating power, and this is the big bad boogeyman.
Yeah.
This is the one that goes through everything. The lead, the
10
cardboard.
centimeters of lead is what you need to protect yourself from gamma.
Oy.
Yikes. So dangerous stuff.
Yep.
The other one we will see in
Positron.
our balancing of equations, I just finished the practice pages myself, is a positron emission. So this is a weird particle. It is a positron. which is
It's
when
a positive electron, basically.
it's basically when a proton undergoes a change, it can become a neutron, which has mass but no charge, and a positively charged charge but no mass. We've taken to name that a positron.
Right, and it really does have the same mass as an electron,
But
which is
yeah.
minuscule,
but the opposite charge.
but the opposite charge. So we call it a positron,
Mhm.
and it's basically the proton losing its charge in one direction and its mass in another.
Yeah, that is a bizarre thing that truly happens. Positrons are created artificially in MRI machines and PET scans and CAT scans. They use this type of charged radiation to bounce off all the cells in your body to see where they are and what they're made of.
Right. We got one thing going for us. Alpha and beta is what we're going to see the most of.
And a little bit of positron in the practice, like 3
In
or
the
4.
practice, what I'm talking about, as far as New
Uh-huh.
York State goes.
Yeah.
Alpha beta is where the game is.
We're going to throw positron at you as a subatomic particle just to
for
throw
fun.
you off. It's like the
Yeah.
distractor. So
Yeah. So know how to use this table O. We just kind of got into it a little bit here. There's different kinds of emissions and different symbols. Let's not get too scared about the foreignness of the symbols and what they look like,
Right.
because they're right on our reference table. We can figure them right out.
And just a note from some of my students who are advanced and moving on into the next unit, they've already done the first POGL. Don't get confused about what a radioactive emission is and what radioactive decay is. An emission is one of these particles that we see on table O.
It was emitted.
And radioactive decay is the umbrella that covers all of the things that could be emitted by the nucleus falling apart. So they are slightly different. I personally think the hardest assignment in this unit is our vocab quiz.
Seriously, because there's so many
Similar, but not
Oh
quite
man,
definitions.
so you got to really study. You know what? I had a student today get 100 on the first try, and I said, "Yo, how'd you do that?" You know what he showed me?
What?
He went and highlighted, literally in his practice packet, the key words that make
For
each definition
a lot
different,
simpler.
and he memorized those key words for that particular definition.
So you saw this definition. Remember, it's a 2-3 word phrase. Boom, done. That's a great strategy.
It was a great strategy.
So thanks
just
for
pass it on.
watching.
And we'll see you tomorrow.
Bye-bye.